is wonderful. I find this really elegant and beautiful, independently of the spin glass story. I just find this beautiful. And this kind of enthusiasm doesn't happen every month. So I think really Panchenko has hit on something very interesting. Of course, it comes after a long story. He's not the only one, but the recent work is beautiful. So I want to talk, so remember where we are. We have these family of models of spin glasses, mixed P spin glasses, either on the cube or on the sphere. I will stay on the cube for the moment. And I described yesterday, and they are characterized by a random Hamiltonian, which is Gaussian centered, and whose covariance is a function of the distance on the cube or on the sphere. That's the core geometrical characteristics. And I described which kind of functions we get. The model parameter was in fact describing this function, and I called it nu. All right, and then we introduced the Gibbs measure, the partition function, and I gave yesterday the Parisi formula, which has been proved essentially by Talleyrand and then improved by Panchenko, which gives the limit of the free energy, 1 over n log of Zn, or at least its mean, as a variational principle, the infimum of a certain functional, which I call the Parisi functional. This functional, of course, is parameterized by the model parameter, by the function nu, which describes the distribution, an external magnetic field possibly, the temperature, and it's a function of the order parameter, which is here a distribution function in the interval 0, 1, or equivalently a distribution function. Okay, we either choose it to describe as a measure or as a distribution function. It is in fact the infimum of this Parisi functional on step functions, which correspond to discrete measures. And I also described how this functional can be extended to probability measures. More general, solving this anti-parabolic nonlinear heat equation, which I described how it was the continuous analog of this stepwise integration backwards that defines the strange Parisi functional. So that's where we are. We have a description of this object. And then I said, okay, the real problems came a little, this is already quite an achievement to have proven that, and I will indicate how we get there with the tools we will introduce today. And I won't have time to get into detail. This is really a huge enterprise. But the real questions come later. You know, you have this variational problem. Can you describe if the minimum is achieved on what kind of measure? Is it uniquely achieved? Can we describe the property of this limiting object? And if we can we say that it is true that this limiting measure is in fact the limit of the distribution of the overlap of two replica? That's the way this order parameter should be interpreted. It's supposed to be the distribution of the overlap of two replica that you've chosen under the Gibbs measure. Under the Gibbs measure, you choose two of them, take the mean under the Gibbs measure of their inner product, the low of under the Gibbs measure of their inner product, and then average under the disorder, and you get a distribution. This distribution should converge to this order parameter. That's where we are. All right, all these questions are very open. Some answers are here, but and of course, one feels that this should give some information about the structure of the Gibbs measure. What is the overlap of two replica? One might think at this point, this is very little to describe the Gibbs measure. The Gibbs measure contains much more than just you take 2 points at random and what is their distance. In fact, Parisi has proposed a very rich picture of the structure of the Gibbs measure at low temperature. At high temperature, not interesting. If Talleyrand hears me saying that, it'll kill me, because in fact, very many problems are very hard at high temperature, which is not usual. But anyway, low temperature, there's this very rich picture by Parisi of an ultrametric structure of the Gibbs measure, and I will try to say what it is. So it seems much richer than just describing the law of two of the distance, if you want, between 2 points chosen randomly under the Gibbs measure. In fact, we will see that it's not, there is something which will allow us to see this ultrametric structure. And I mentioned it yesterday. That will be the Ghirlanda Guerra identities. So yesterday I explained this way of going to the limit. You take the Gibbs measure, which is a measure on the sphere, right? In fact, on the vertices of the cube, but that's, if you want, on the sphere of radius square root of n. You have this measure, and you could do that for any measure. It has nothing to do with spin glasses, right? Take a measure on Rn, any measure. Right? Now you create, so let me remind you what we did. We create the overlap matrix, which is the following. So I take sigma L, a sequence of an IID sequence with distribution Gn. Gn was my Gibbs measure to the infinite. That is, you choose an IID sequence. Each replica is taken with distribution Gn. All right, and it's infinite. Then you create the infinite array Rn L prime to be simply so sigma L inner product with sigma L prime. Right? It's the, and maybe here we could take 1 over n that, which is the, because that's a usual convention. So that's, if you want, it's the overlap, as we define it, of the two replica. Right? So you take the infinite matrix of overlaps of all these points. So you see that this is in a space that I think I call M, which is simply, look at it as the product of R over all possible. So this whole matrix, Rn, belongs in that. All right, you can equip, of course, this thing with many different topologies, and that's not an innocent choice, but here we do something as simple as possible. We will be essentially only concerned by the finite dimensional distribution of this guy. So we put here the pointwise convergence topology. Remember that, in fact, our Rn's are bounded, right, by 1 in absolute value, between -1 and 1. So in fact, this lives in the product of 0, 1. So this lives in a compact space. Okay? So the distribution of Rn on this, say equipped with its Borel subsets, are tight. This is not a deep statement, it's just trivial. They are tight because they're all carried by a compact set. Right? An infinite product of compacts is compact. Okay? So there is no doubt now that this is tight. So we can now consider the set of possible limit points that will be convergence along subsequences, possible limit points. That is, distributions on this, right, which will be the possible limits. So for those used to statistical mechanics, we've done the following, which I explained last time here. We created one space, which is this space, on which we have, which is fixed, which does not depend on n, on which we have random objects whose distributions here are tight. So then they will converge along subsequences. Whereas initially, of course, we couldn't do it because the Gibbs measure was on a space of dimension n, and n was changing. Right? It's -1, 1 to the n. So in some sense, we have here a kind of global description of the Gibbs measure on one given space, and for which we can study the limit. Of course, what we would like is that there is only one limit point, And then we'd have convergence. Yesterday I also explained, so before we go further, you may think, and I explained that yesterday, so I know that pedagogy is repetition, so let me say that again. You may think initially that when you do that, you lose a lot. That in this matrix here, you don't have the whole information about the Gibbs measure. In fact, you do, up to a point. I explained how yesterday. If you have this infinite matrix, take its upper left minor of size m, right? M by m. M has nothing to do with n here. M will be huge, all right? Now, here in this matrix, you can count. You can look at, so on the diagonal, you will get 1, right? Because when L equals L prime, this is 1. But you will have 1s elsewhere outside of the diagonal. Every time two replica, sigma L and sigma L primes, L prime are in fact equal, which will happen, of course, because you only have 2 to the n points on the cube. So if you take m much larger than 2 to the n, you will have repetitions. So every time you have the same replica, of course the overlap is 1, and you find a 1 somewhere. So very easy now. You group your replica according to the fact that they give a 1, because you know that they correspond to the same replica, to the same point on the cube. Right? What am I explaining here? In this object, you don't see the initial space at all. You would find the same space here, whatever the Hilbert space you started from. Here we started from Rn, you could have started from any Hilbert space, and you would still have this object. So what I'm saying here is that you find, now by regrouping the replica like this, in some sense you reconstitute the space, which is missing here. Then you have blocks, which you have 2 to the n blocks, all right, which correspond to the same replica. And then by looking at the block, looking just at the size of the block, letting m to infinity, the law of large number will give you, the size of this block will give you the Gibbs weight of that particular replica. So from this information, you can reconstitute all the Gibbs weights, the 2 to the n Gibbs weights. What you cannot really reconstitute are the cube, right? It's not there. What you have is the information about the Gibbs measure up to an orthogonal transformation, right? Which is natural, because as I explained yesterday, the Gibbs measure, the distribution of the Hamiltonian is invariant by orthogonal transformation. That's because of the structure. The covariance is only a function of the distance. So it's invariant by orthogonal transformation, which means that the Gibbs measure is essentially invariant by orthogonal transformation too. Not exactly. If you take a cube, if you take the Gibbs measure on the cube, if you apply an orthogonal transformation, then the Gibbs measure would be preserved, except that the place where it is supported, this will be a rotated cube instead of the initial cube. So you lose the space itself, but you don't lose the structure of the distances between the points in this space. Okay? And if you're interested just in the Gibbs weights, obviously this contains it. So that was just a caveat. We haven't lost the information about the Gibbs measure here up to orthogonal transformation. It is included in this information. It doesn't mean that it's simple, because you realize how I explained how to do that. Mathematically, it means you have to regroup and then to take a limit. So it's not a trivial object, but the information is there. All right? And in fact, at the very end, we could go back from the information we get for these limit points to something on the spins themselves. All right? But that could be done at the very end. It should not be a surprise that it can be done, because I just told you why. Now, the question is, once you agree that this is the right object to study, the question is, study this. What are the possible limit points? What can we say about them? Is there only one? What kind of structure do they have? All right, that's the usual problem of studying Gibbs measure. So those possible limit points, Panchenko called them asymptotic Gibbs measures, which is not absurd, but and even a good, but kind of loses the fact that it lives in this space of arrays of inner products. And essentially, it's the same as what was called before ROSTs. So this thing was random overlap structures. I long wondered why there was a small t here and not a large t. I have no real idea. I believe that it might be because of our esteemed colleague Rost with a big T, I mean with the 4 letters in the same case, and that maybe they don't want to make a pun on that. So this is random overlap structure. That's the same thing. All right, so what can we do about these guys? So now we attack this problem purely as mathematicians. Let's forget physics and all this, because you just want to do the natural thing that a mathematician does, that is look at the invariance properties. Once you do that, you know you are doing something interesting, if you can conclude just with that. So what kind of things are constraining the possible limit points? So here are the properties that I listed yesterday. Okay? So first, it's clear that, so this is a Gram matrix, right? It's a matrix of inner products. And we're taking a limit, and we want to see what, it would be nice to say, for instance, in the limit points are also Gram matrices. But there is no reason for that, right? Okay, so, but because it's a Gram matrix, if we could say the limit is a Gram matrix, we'll be done. But we cannot say that, but let's take some property that come from the fact that it's a Gram matrix and see how they go to the limit. The first thing is that, of course, it's a symmetric array. Second, it's non-negative definite. Or maybe I should first, second, third. First, it's weakly exchangeable. So for the moment, bear with this weakly, because you will see what strongly would mean later. Second, it's symmetric, and third, it's non-negative definite. Right, so weakly exchangeable, remember what that means? It means that if I take any random permutation, any permutation of a finite number of indices, then the distribution is the same, right? Because if I simply label differently the vertices of the hypercube, I get the same thing. Right? Obviously, this is again a consequence of invariance by orthogonal transformation, because that's an orthogonal transformation. Okay, so that's weakly exchangeable. Symmetric is clear. It's an inner product. So inner product of L and L, sigma L and sigma L prime is the same as you revert the order. And non-negative definite is, of course, clear because it's a Gram matrix, right? So everybody knows that, right? That's linear algebra 101. So these are the properties. And these properties here all depend, the important thing, as I explained yesterday, and now I'll begin the new lecture, all these things depend only on the finite dimensional marginals of the distribution, right? They are not very complicated properties. You can test whether these properties are true or not by just taking a finite chunk of the matrix. Remember, this matrix is infinite. So even with this very simple topology, which was just point by point, then if something is true for such an object, it will be true for any limit of an object, right? So these properties are satisfied by all the possible limit points, right? All right. With that, so can we conclude from this that that the limit is a Gram matrix? It's a distribution of a Gram matrix. So you see what I had. I had a Gram matrix. I weakened it by just keeping these properties and saying, does that imply that the limit will be a Gram matrix? Right? It will be the distribution of a Gram matrix. Okay? Remember, Gram matrix simply means the matrix of inner products in a Hilbert space. Right? So the answer is almost yes, very surprisingly. Almost yes. And that's quite a feat. So why is that? So why is that? So the answer is, I'll give a precise statement, but the answer is almost, that is a distribution that satisfies this on the set of infinite arrays like this, in fact, is a mixture of gram matrices for IID objects. So here we start with a gram matrix for IID objects. All this is independent of Gn. Gn could be anything here. Right? A priori, so you take the gram matrix, and then of IID things, you go to the limit, and the limit is just a mixture of such things. And it has to be. Right? So that's really interesting. So this theorem is called, so that's the Dov-Bish, Sudakov representation theorem. Which has been put to use for this purpose here by Panchenko very well and reproved, simplified. So let me explain what that is. So it says in some sense, let me say that in words, any distribution on infinite arrays that satisfies these three properties is a mixture of IID arrays, gram matrices. Okay? That's in words. So now let me put that in more mathematical things. So just for those who, this is for the younger part of the audience, what do I mean by mixture? It's, take a probability P here on my set M. It could be on any set. This is my set of infinite arrays. And it is a mixture, if I can write it like this. P of A is the integral of Q of omega and A. Let me not call it omega. U and A. D mu of U on the set U, where U, let's say U mu is a probability space. And where Q, so that's one thing. Second, Q of U dot is a probability on my space, probability measure on my space M. And M could be anything again. And third, Q of dot A is U measurable for all A. This is for all U. This is for all A. Okay? So in words, for those who've never seen what a mixture is, it says P is simply obtained by taking, so these guys are probability measures, indexed by something, and then you average on the something. Right? Another way to say that is that this is a random, this thing is simply a random probability measure. Right? You have this thing is a random probability measure in an external randomness parameter U, and you just average on that. That's the mixture. All right. So, of course, you're happier when this mixture, when this auxiliary space U is finite, for instance. This is a nice mixture because you just have a finite mixture. Now, I will say that Q here is generated, so a probability on M is generated by an IID sample. If it can be created as over there, right? That is, so, but here, so let me, here I want to add this extra parameter, Q, right? This Q with a U here. So that means that it is the distribution. So there exists, let's eta, which is a probability measure, probability distribution on a Hilbert space, a separable Hilbert space. So I will, here I choose L2, but it could be any separable Hilbert space, cross R plus, such that the Q, this Q is the law, the distribution of HL inner product HL prime, like we have over there. And here is a twist. I have to extend a little bit what is over there. So when I said that it was the statement I gave before, I put under the rug one difficulty, which is now coming. Okay. So, and here HL and AL are IID distribution eta. Let me just. All right, so you see it's very similar to what we had over there, inner product. But with a twist, that is, I change what's happening on the diagonal. I add IID stuff on the diagonal. Right? So it's a more general object. And you could think, why do I need to do that? If I start from this, maybe I should stay with. Over there, remember, on the diagonal, everything is 1. Right? So why do I have to add things on the diagonal when I go to the limit? How is that created? Usual thing. If you start over there from things which live on a sphere. It's perfectly possible, and it will happen, that in the limit, the thing is no longer concentrated on the sphere, but on a ball. So then you lose the fact that the norm is constant, and then you have to compensate for it. That's what this thing does. All right? So this is what an IID sample is. And so the theorem of the Dovbich-Sudakov representation says is allow P on my space M of any gram definity array, so, or matrix. So I didn't say what that means, gram definity. Gram definity means this. You know, so if you don't want this name, just say satisfying the property 1, 2, 3. Okay? Is a mixture of laws generated by IID samples. All right, so that is, you have this formula. So it means that in star, QU is generated by an IID sample. Right, which means there exists an eta U. So another way to say that is the following. So equivalently, there exists a random probability measure, eta, so now it's random, it's eta depending on U if you want, on L2 cross R plus, such that the distribution of RL prime under P is the same distribution as what I wrote over there, HL, HL prime, plus AL, indicator of L equal L prime. And conditionally on eta, so eta is random. When you fix it, then the sequence HL AL, which is on L2 cross R plus, is IID with distribution eta. Okay? This sentence is just exactly the same. This blackboard says the same thing as the other one. I'm just saying now. So now let's compare what we've done. We start with a gram matrix generated by an IID sample on Rn, here on the sphere. We take the possible limit points, and by just identifying the three properties 1, 2, 3, which we'll call gram definity, we're saying that the limit is the same structure, up to a twist. First, so it's something of the same nature. It's an inner product. Right here you have to realize I put an n here because I could have not put an n, but I put an n so that these overlaps stay bounded. Once you put this normalization by n, the overlaps stay bounded, you stay on the unit sphere, and then of course then you have a chance of having a limit. So here we have these guys. Obviously, in our case here, this is general, but in our case, when these guys have a norm bounded by 1, these will also have the same thing. So the support of the distribution of these guys will obviously be in the unit ball of L2, not necessarily the unit sphere. And so you have the same thing, except that you have to add something on the diagonal, maybe. Right. All right, so that's very remarkable. It's the same structure, except that this, okay, forget about the diagonal, we'll deal with that later. But except that now the distribution of this guy is itself random. It's a mixture, right? Which is not a big deal, because in fact, if you remember, this distribution was random also. Right? So in some sense, the distribution of this random measure here, when you look at it on L2, if you could forget about this part, should be seen as the limit of the random Gibbs measure on the sphere. Right? So that's really the important object that we want to understand. All right? So that's a very nice theorem. Okay, so questions about the statement? Do you understand the statement? Oh, yeah.
In the limit, is our measure eta really just, in essence, going to be just a measure on L2 because maybe the sequence AL is just going to be 1 minus the norm of HL?
Yeah, in the limit, in most of the cases, you can construct, of course, this theorem is extraordinarily general, so you can construct everything. But in the context of spin glasses that we'll deal with, this guy will not be there. So it will be concentrated in something, and then you can get rid of it. And so essentially, you need to understand just the part on the H's, you're right. Okay, but at this point, we can't escape that. So this theorem is really nice. So again, let me say that in even less words. This says there exists a random measure on the unit ball, in our case, where everything was bounded. There exists a random measure on the unit ball for our ROST, our random overlap structure. There exists a random measure, say G, on the unit, G like Gibbs, on the unit ball of a separable Hilbert space, here L2, such that essentially the distribution of R of L and L prime is exactly the gram matrix, at least when L is not L prime. All right? That's beautiful. So this theorem is beautiful, but it comes from a theorem that I have always neglected. Every time I have taught probability, and I can tell you I've done that quite many times, I tend to jump over this theorem. And it's my great shame now. It took 30 years to realize that was more interesting than what I thought. So if Percy Diacon is here, this will kill me. Okay, but you can admit, there's a culture also. That's okay. And a side remark. Probability, I mean, it's the same thing for mathematics in general or science probably. There are traditions which are, I think, in the bricks of the buildings where things are done. There are groups and cultures in probability. And clearly, there's one in Europe, which is different from the rest and tend to emphasize a certain type of things. And in the US, I don't know about where Brazil would fit, but in the US, there are two cultures, which are working together, of course, but are slightly different. And you have the West Coast and the East Coast. It's not the same. Obviously, exchangeability is a West Coast thing. I don't know, in fact, if Definity ever worked in the US or how it went there, but Aldous and Percy, of course. All right. This doesn't work, of course, because Percy is an East Coast guy initially. But all right, so what is this theorem? The theorem is, of course, Definity. So I won't prove any of these, but in particular for the younger part of the audience who might not know that, let's go there. So the theorem says the following. So first, instead of looking at arrays here, let's look at sequences. So you look at a sequence of random variables, say SL, has an exchangeable distribution on any reasonable space. If for any, say, pi, which is a permutation of a finite number of an index, if you look at sig S of pi of L, it has the same distribution as S of L. Okay, that's exchangeable. If you change the labeling of the variable for a finite number of them, you don't change the distribution. Obviously, this is true if the SLs are IID. All right? So and the theorem of Definity says any exchangeable is a mixture of IID. Okay. Exactly like before. So you take an exchangeable mixture on the space of infinite the distribution on the space of infinite sequences, which is exchangeable. It's a mixture in the sense of I defined before of IID distribution, of product distribution. Right? This can be even given a little more precisely. In fact, you could say that this SL in distribution is the same as G of W and UL. This W here will be the randomness of the mixture, what I called U before. Maybe I should call it U. Yeah, why not? I have ULs, I can call it U. So this is my U of before, the parameter of mixture. And these guys are the IID things. And so G is here a measurable function, a Borelian function from 0, 1 square to R, measurable. And the U and ULs are IID uniform. So here I go a little further, but this is for free, because as you know, any distribution of one random variable can be seen as a function of the uniform distribution. Right? So you take any exchangeable mixture, any exchangeable distribution, it's obtained like this. If you one given function of one uniform and then a sequence of IID uniform. Good. All right, now, next step. So the next step is to look at the Aldous-Hoover representation theorem. So now Aldous and Hoover here are concerned. So that was in the 50s, I guess, Definity. This was in the 80s. And by instead of sequences, by arrays, by infinite arrays. So you look at an array, SLL prime, infinite, as before, of random variable, or matrix of random variables. And you say that it's exchangeable. So what does exchangeable mean? Exchangeable here means that if you take any two permutations, finite number of indices, then S of pi of L, rho of L prime, has the same distribution as S of L, L prime. So this means you can permute to your liking the rows of the matrix and the columns of the matrix with two different permutations, and you get the same distribution. So that's a strong statement. That's why before we called it weakly exchangeable, because we had the same permutation for the rows and the columns. And you see why. It's important. In our case, we don't have strong exchangeability like this, because the labeling here is the labeling of the points on the cube. And you can't permute them. I mean, if you change one, then you change the other in the same way. There is no way you can do that, right? So we cannot have this. So this is not yet what we need. But that's this notion of exchangeability. And the theorem of Aldous and Hoover is very similar to the Definity theorem. It says that any exchangeable array, so theorem, the distribution, or let me say, any exchangeable array is equal in distribution to the following thing. A function g, I need four variables now. U, UL, VL prime, XLL prime. So where g here is a measurable function from 0, 1, 4 to r, because I have four variables. Where now the u, the ULs, the VL, and the whatever else, the XLs, are all IID uniform. Okay. So you're saying to create such an exchangeable array, I generate uniform random variable, and I just take a function of these. Important to note that here I have L prime, and here L. It's of course not the same. UL, VL prime, XLL prime. All right. So with this now, no, they are LL prime are just integers from 1 to infinity.
Yeah, but each L is associated to a replica.
In this model, yes.
Even in disorder.
No, not a configuration in the disorder. No, forget the disorder. It's just, you could have done that for any kind of GN. It's just the index of the repetition in the IID sample you've generated from your measure, that's all. Your measure, you have a Gibbs measure, you generate an IID sample, and L is just the number in this IID sample. Nothing to do with the disorder.
Yes, I see it. But then when you say you do some permutation
Look, it's written here. L here. So when I permute this, oh no, I'm sorry. This is, no, I'm sorry. Okay, I get your question. So if I do any permutation, here I started from things which are IID. I'm sorry, you're completely right. I withdraw what I was saying. I was thinking of something else. Here, I have an IID sequence of things under a given measure. If I take a permutation of a finite number of indexes, the first 17, it stays IID. What I meant was not about sites. You're perfectly right to point that. It's just that this is an inner product. It's a function of these two variables, right? So I cannot permute the L's in one way and the L primes in another way. Right? If I just do the same permutation for the two guys here, of course, I'm just using the fact that it stays IID. I'm sorry, you're perfectly right. That was wrong. Okay, so so now the next step is the following. So if so this is really if the array S is symmetric. So for the moment we've used the exchangeability in a strong form and weakly exchangeable only. So weakly exchangeable is what we used before. That is, for any permutation pi with a finite number of indices, R of pi L, the same pi is in distribution R of LL prime. It's weakly and symmetric. Then, in distribution, we have SLL, I call it R here, I'm sorry. I had to call it S. SLL prime in distribution, the array is the same as G of W UL when L is L prime plus F of W, or U I call it, U, UL prime XLL prime when L is not equal to L prime. And G and F is, G is a function from 0, 1 square to R. F is a function from 0, 1, 4 to R. And measurable. And F is symmetric with respect to its two central arguments. So F of U, V, W, T is the same as F of U, W, V, T. Right? F is symmetric in those two arguments. Right? And of course, U, UL, XLL prime are IID uniform. So see the difference here. If when you push the structure, you just want it to be weakly exchangeable but symmetric, then you need one less. Over there we had one more sequence. You had UL and U and VL. Here we have only one sequence, which we'll repeat here. UL prime. Here it was UL VL prime. Okay? So you put the same sequence here. You correct on the diagonal by something, and you get any weakly exchangeable symmetric thing. So at this point, we're now not very far from, so this is the Aldous-Hoover theorem, from the Dovbich-Sudakov theorem.
Don't you need EX, LL prime to be symmetric?
Yes. In fact, let me say that this is only for L smaller than L prime. Okay, and then you get everything by symmetry. Okay, that's why, of course, you need the symmetry to be able. All right, so there we are very close to the Dovbich-Sudakov thing. We have put in our model the fact that we have a weakly exchangeable array, a symmetric array. So what is missing in this property? The non-negative definiteness, right? So the next step is when you go from here and you add the non-negative definiteness. So the next theorem is if add the fact that S is the property of non-negative definite, for S, right? By the way, I keep saying that. Everybody knows what that is, right? Okay. So, of course, by that I mean non-negative definite for every finite part of the matrix, finite. Then you have Dov-Bish-Sudakov, which simply means that this. So look at the structure. It simply means that this F here can be seen instead of this general thing as the inner product of two vectors on a Hilbert space. And we have this correction here, which is just the AL. Remember I had the AL, it's just this. So when you add positive or non-negative definiteness, then you have to work, it's quite a theorem, to prove that this can be replaced by this inner product. All right? So I don't go more into that. That's interesting. So let me summarize. That was just an excursion into this exchangeable theory. So let me summarize where we are. We start from our overlap matrix, and we end up with a collection of measures which are Dov-Bish-Sudakov type. That is, finally, we end up with any one of the limit points is given by a random measure on the unit wall of a Hilbert space, right? And from this random measure, Hilbert space here being L2, from this you generate the Graham matrix, and this will be this limiting object. All right, so at this point, and I'll stop for a few moments now, at this point we have this description, we have this Dov-Bish-Sudakov measure somewhere on L2 or on any Hilbert space you want. The next thing is this is not yet very constrained. We don't see, for instance, in what I've said here, the measure, the function nu, which was describing the model, the beta p, for instance, there's no difference between a p-spin model with p equals 5 and p equals 17. Right? You do this whole thing. Where do you see that it's 5 or 17 in the limit? Right? It should be seen somewhere. So how do you see the influence of this function nu? So we know how. This function nu appears in the Parisi formula. So it should be there somewhere. So as I explained last time, and again this morning, and then I will do that again, when you have a distribution of such an infinite object, what is really important is at least you could look at the distribution of one overlap. This thing being exchangeable, the distribution of one element of the matrix, not on the diagonal. One non-diagonal element, right? And they're all the same by exchangeability. This will be, as I said, the order parameter. This will be the thing that you try to minimize on in the Parisi formula. But then you could also look at the distribution of 2 points in the matrix. It means 2 distances, or 3, or 4, or 5, or 10. Right? So we will see after the break that there is, if these limiting guys satisfy one more thing, the Ghirlanda Guerra identities, then everything becomes nice. That is, the whole distribution is determined by the distribution of one element, which is astonishing. Second, in fact, the overlap are necessarily non-negative in the limit. That's the Talagrand positivity principle. In fact, the diagonal elements are not bothering us, so we can forget them. Right? And finally, that's the Parisi main conjecture. The structure of this random measure is ultrametric. There is a tree hidden somewhere. All right? So that's the program of the next hour. To state that, to prove that would be the next year. But okay. So now that we have the Dov-Bish-Sudakov theorem, we know that we want to study we know that any weakly exchangeable symmetric non-negative definite array is in distribution the same as a random measure on of a gram matrix of a random measure on a Hilbert space. So we want to study this. So let's consider G now. This is what, that was the distribution of what I've called the H's before. So G will be a random measure on the unit ball. It could be, you could forget that it's bounded, but for us it will always be bounded, of a separable Hilbert space, which for us was L2, and every separable Hilbert space is essentially L2. Okay? So that's what we get, right? From the Dovbich-Sudakov theorem, we know that any limit point of our arrays here will be given by, at least out of the diagonal, by a random measure G on the unit ball of little L2. Right? So we have this. I will denote by brackets here to follow the tradition of Talagrand, Panchenko, and all that, that this will be the average with respect to the measure G to the infinity. Right? So it's the same thing as done here. You take an infinite sequence of an infinite IID sequence under G, and this bracket will mean the average under that. Right? This average here means that you haven't yet averaged on the disorder of G. Right? So what this means is you've taken sigma L, an IID sample under G with distribution G. And you look at the overlap, which is given by sigma L, inner product sigma L prime, where now this, of course, this inner product here is the inner product in the Hilbert space H. All right? You look at this thing. For the moment, let me forget the diagonal question. And let me define, so I have this, I'm not sure I will need that for the moment. Let's forget it. Yeah, I need a notation. RLL prime is this. It's just a notation. So I look at this, as I did before there, I look at this infinite matrix of this infinite gram matrix defined by this measure. So it's a random matrix because G is random. So I'm exactly in the same situation I had here. Right? Here I had my unit ball was in fact the unit sphere of Rn. Right? The measure Gn was carried in fact by the vertices of the hypercube. So that's exactly the same construction. But now I do it in general in a Hilbert space. All right, so let me define the very important property, which is the Ghirlanda Guerra property or identities. Or maybe, yeah, identity. So we said that this random measure satisfies the Ghirlanda Guerra identities or property if the following is true. For any n, maybe I should call it, yeah, for any n, for any function f, which will be, say, bounded and continuous, for any function psi, which will be bounded and continuous, then you have the following. Expectation, so this expectation means expectation under the disorder of G, of f. And this f is a function of R, of all the RLL prime, when L is different from L prime and less than n, times psi of R1 n plus 1. This is equal to 1 over little n expectation of mean of f plus times expectation of psi of R12 plus 1 over n sum from L equal 2 to n of expectation of bracket of f of psi of R12, f of the same thing, psi of R12. So this looks like a crazy identity. It takes a while to absorb it. But you will see that it's not crazy at all.
Do you also have brackets in the first expectation, right?
Yes, yes, yes. Thanks. All right, first it takes you time to write this down. Then it takes some time to understand what it means. But it's not at all crazy. You will see what it means. So first let's read it. Okay, what is that? You're taking here a mean under the Gibbs measure, under this G, this random measure. Then you take the mean under the randomness. Mean of what? You take here one observable, which is a function of the whole. So you have your infinite matrix R. You're taking a size n. Okay, and then so here you have R11, R and n, which are in fact here numbers between 0, smaller than 1, and then R12, etc. This matrix is symmetric, and it's exchangeable. So the distribution of this element or that element or that element is the same. The distribution of any pair of elements is the same. All right? So now you look at this collection here, a function of this whole matrix, this whole upper quadrant here, except the diagonal, maybe. Right? So it's a function of all these guys. All right. And now, so you have this n by n system. N equals 17. All right. And now you want to understand what's happening if you add one replica. Right? So you add one replica. You want to go to this matrix if you want. And you're asking yourself, so you're not interested yet by the diagonal elements. You're interested by the distribution of each of these guys first, right? They're all the same, right? Easy. They are the same as the one before, so nothing. But now, how do you relate the relation of the overlap R1 n plus 1, which is here, with respect to all the other ones? That's what this does. You take psi of, so the distribution of R1 n plus 1 is the same as the distribution as R12. No big deal. But now you assume that you know the distribution of all the pairs here of overlaps, the distances between all the points. And you want to understand the joint distribution when you add one more point. Right? This is what this is doing here. You have a function of everybody, n points. And then you add one more, and you want to have the joint distribution of the distance between site 1 and n plus 1 when you add this one. And what this says is it's a mixture of two terms. Here, it's completely decoupled. Right? You have f here, R1. So I could, instead of 2 here, I could put n plus 1 if I want, because it's the same. Right? And then here I have something different. So let me say what this means, now that we've read it. So equivalently to this, what this says is the following. The Ghirlanda Guerra says that conditionally on on the values of these overlaps R, L, L prime, when L and L prime are smaller than n, then the distribution of R1n plus 1, when you add this new guy, is the mixture one over n zeta plus 1 over n sum from 2 to n of Dirac mass at R1L. So I didn't say what zeta is. Zeta here is what will be called the functional order parameter of my measure G, and it is simply the distribution of one guy. So zeta is a probability measure on R, and it's given by, take the mean of that, of the set of a replica, if you want, sigma 1, sigma 2, such that their inner product is in A. Okay? So zeta is the distribution, if you want. Zeta is the distribution of R12 under E this. Right? Or if you want, under E, because there are only two replica, under EG2. All right, so it's the distribution of one element. Under the Gibbs measure, you choose two replica under the Gibbs measure, and then you average under disorder. This is what we expect will be minimized by the Parisi, in the Parisi formula. Right? So if you take an array like this, the first thing you want to look at is, of course, the distribution of one element, one non-diagonal element. We call this zeta. Okay? Now, look at what this says here. So first, check that this is the same as this. Take the 2 minutes or the 10 minutes, depending. It takes to check that. This thing, if you condition on this whole matrix, here I'm computing the distribution. If I can compute that, I'm of course able to compute the distribution of R1n plus 1 conditionally on these guys, if I can do that for any f. Right? So look at what this says. It says that here I get the, this is just zeta, because of course in order to compute the conditional distribution, I should divide all this by that. Right? So here I get zeta with an 1 over n, that's the first term. And here what do I get? If I divide this by expectation of f, right, I get just the Dirac mass at R1L, and normalize also by 1n. Okay? So this is the, there was an L here, I'm sorry. L. Now, what does that mean? Geometrically, it's nice to see a formula like this. For me, it took me a long time to swallow the Ghirlanda were identities for a long time since I was not really looking at them. It was just this huge thing that I didn't even want to read. Because I don't know about you, but my brain cannot swallow a formula that long. Then when the formula comes like this, it's already easier to swallow. And once you have a picture of it, it's clear. It's then very simple. Imagine for a moment that in fact G, let me give you the interpretation of that. If G is carried, is G is supported by the sphere, just right, so that we have something simpler. We don't care about the diagonal at all. So if it's supported by a sphere, say the unit sphere, but by any sphere in H, that is under G, the norm is constant, right? All the vectors of the norm. Then, so the norm of the sigma L's are all the same. Say is a constant C. Right? Just imagine that. Then, of course, it's easy to compute the distance between two objects. So let's say 2 points. The distance is, of course, simply, right, the distance square if you want. This is sigma 1 square, which is C2, plus sigma 2 square, which is C2, minus 2 sigma 1 sigma 2, which is the overlap. Right? So it's simply 2 times C square minus the overlap. Okay, so knowing the overlap, we will use this thing constantly, and I've already said that many times. The overlap and the distance is essentially the same thing. Right? So knowing the overlap is knowing the distance. So what is that saying? That it means the following. You have the following. So once you have this remark here, it says the following. You have endpoints on this unit sphere. Again, it's hard to draw endpoints in dimension infinite, but so you have these endpoints on the sphere. And you know the distribution, the joint distribution of all their overlaps, or equivalently, if you're on the sphere, the distribution of all their distances. Okay, you know all these distances, and not only, so the distribution of each distance is essentially given by zeta, up to a trivial modification, by the functional order parameter. But you also know, let's say, the distribution of jointly of all the distances. Right? So for Vladas, I'm trying to explain what the Ghirlanda Guerra mean, and the simplest case is to assume that G is supported by a sphere. We will see that this is not a hard restriction at all. In fact, Ghirlanda Guerra implies that it's supported by that. But so if it's supported by a sphere, then knowing the overlap or knowing the distance is the same thing. So we can think in terms of distances. So now I'm taking endpoints on the sphere, and I'm supposed to know the distribution of joint distribution of all the distances. Now I want to add one more point, which is the n plus 1 point. Now I condition on all those distances. Again, not the position of that. That's the rule of the game. We don't want to fix the position. We want to fix the collection of distances between them. All right? So any isometry would not change that. I add one more point, and I'm saying now, what is the distance between this and one given point? Right? Here I chose 1, but I could have chosen any other. Right? So what is the distribution of this distance? Okay? Of course, what I'm going to say now will not be true on my picture. But what this says is the following. You have two ways to choose this distance. It's a mixture. With a certain probability, you choose it with no information, just under the distribution zeta. Right? As if you didn't have the information on, because remember, we have condition on those distances. So the mixture is, okay, one possibility is to ignore this information and just choose it under distribution zeta, as it should be, right? If you don't condition, the distribution of this distance is zeta, right? This is what zeta is. It's a distribution of one distance. So one possibility is forget that you have condition, forget all this information. I don't want to know it. I just choose this as a usual thing. The other possibility in the mixture, so don't worry for the moment about these factors. These factors are just imposed naturally. Right? So forget them. Think of this and that. So I just described this first possibility. You choose zeta. And so you flip your coin. The other possibility of your coin is that what you do is you simply look at all those distances here. Right? You exclude L equal 1, of course, here, because L equal 1 corresponds to the distance from 1 to 1. So you look at all those distances here, n minus 1 distances that you have with this guy. And you decide that this new side, if you want, that you're adding to this, will be one of them. That's what it says. Then the fact that you have 1 over n here and 1 over n here is clear. Because what is the mass? Forget what the coefficients are here. What is the mass of this probability measure? Count. N minus 1, right? The mass of this is 1. The only possibility to add them up in such a way that you have is 1 over n and 1 over n. Okay? So forget about the coefficients have to be like that. That's not a big deal. The important thing is this and that. It means something very extreme. Yes?
Yeah. I found also hard to swallow after we clean the formula and after we explain with the picture is that it's like it's annealed. So you know those distances, so it's telling you something about the disorder, but at the same time, you know, there's this 1 over n zeta there, which is like just ignore all you learned.
Yes?
And you get you sample it annealed again.
Yes? It's a crazy property, which I'm now putting forward. It might be never satisfied. All right? The truth is that it's always satisfied, at least approximately, for all the spin glass models. And that's Parisi's genius. That's the intuition that was incredible and is still incredible because of this thing. So that's a fact. So let's postpone for the moment. Let's forget spin glasses. Forget all that. Forget what. I'm just saying this is a property. What does this property mean? And I'm just emphasizing precisely, to go in your way, that it's a very hard, very strong property. It says something very bizarre. It says, if you have n points, I want to add 1 point. I condition on the distances of what I know. And now the distribution is simply, I want to either completely forget the information, and I choose the distance with the distribution zeta. So I want to ignore the information. Or I want to completely absorb the information, which means I choose the distance as one of the distances I already have. And of course, then if I choose one that I already have, I have to weigh them with the same weight because of all the exchangeability. Right? So I'm saying the following thing. I'm extremely conservative. Every time you give me the information about n points, the next distance I choose is one of them. And sometimes I choose to say, okay, I don't want to know. I just choose it completely randomly under the natural distribution. That's what Ghirlanda-Guerra means. Okay? Once you've understood that, you can reconstruct the formula. Yes?
And sometimes you're not even using all the information because you're just using the distances from the single point. You're not using the distance from 2 to 3.
No, that's right. You're just using this, but you're conditioned by the whole thing. Okay? So that's what Ghirlanda-Guerra means. The consequences of Ghirlanda, so you can imagine that coming up with this was a great feat, in fact, coming up with the idea. So there is a long history. It didn't happen simply that Ghirlanda and Guerra came up with this and then it was the aha moment and suddenly everything was clear. It took a very long time because you had competing things which were in the same word. You had the Ghirlanda-Guerra, the Eisenman-Contucci stability, some extended stability, all sorts of things, ultrametricity. It was not clear which was implying what. All sorts of proof were done in one way, another way. Now we know the Ghirlanda-Guerra is the basic thing. Once you know Ghirlanda-Guerra, everything follows. All right, so here is some of the consequences of Ghirlanda-Guerra property. So, all right, so assume again that the support is carried by a ball, by a ball. I'm sorry. So not a sphere. The sphere will come later. So I'm in the case where I have my random G carried by I just erased it. Carried by the unit ball. All right. So here are some consequences, and suppose that G satisfies Ghirlanda-Guerra. G satisfies GG. All right, then first theorem. Let's look at Q star. So you can define zeta, the functional order parameter. Let's look at Q star. Physicists call that QEA for Edward Anderson, but let's call it Q star here. Q star to be the maximum of the support of zeta. So you have this functional order parameter, which is the distribution of the overlap. You look at the maximum of the support. Q star is, of course, smaller than 1, right? Because the support is between -1 and 1. You call Q star this maximum. This will play a very big role. So first thing, with probability 1 in the disorder, G is in fact carried by the sphere of radius Q, square root of Q star. Okay? So if you start by a measure which is on the ball, unit ball of L2 or a separable Hilbert space, if it satisfies Ghirlanda-Guerra, in fact it is carried by a sphere. Of course, of radius smaller than 1. This Q star could be 1, could be smaller than 1. So what I said here was not a restriction, as you see. It's in fact implied by Ghirlanda-Guerra. So when you have Ghirlanda-Guerra, talking about overlaps or distances is the same thing. Theorem 2. So all these theorems are under Ghirlanda-Guerra, otherwise it wouldn't be true. The theorem 2 is called the Talleyrand positivity principle. The support, so the result is the support of, this is 1, or equivalently, the support of zeta is included in R plus. This is very interesting. It means when you have Ghirlanda-Guerra, the overlaps are necessarily positive. Okay? Third, so now we know the support of zeta is between 0 and Q star, right? The Gibbs measure is carried by the sphere of radius square root of Q star. But now we know much more. Let's say theorem 3. So I think this now, at some point what I'm saying is really due to Panchenko, and I'm sorry, but I'm not sure. This is due to Talleyrand, but this, all the rest I think is due to Panchenko. So under Ghirlanda-Guerra, the distribution of the whole array, so this is what I announced last time, is determined by the distribution of one element, that is by zeta. All right? So let me say that again. By the Dovbich-Studakov theorem, the limit points of these guys are something like this. You know, a random measure on the unit ball of L2. If it satisfies Ghirlanda-Guerra, which of course we don't know, then first it's supported by a sphere. And the overlaps are positive. And in fact, this parameter zeta, that's why we can call it the functional order parameter, determines the whole distribution of the array. All right, and then theorem, which is really the crowning achievements, and this is definitely by Panchenko, 4. If Ghirlanda-Guerra, of course, then the distribution of R is ultrametric. And that's the Parisi, if we can prove Ghirlanda-Guerra, then this is really the Parisi ultrametricity conjecture. So this is big. So let me say what ultrametric means. I have to spend, so maybe I could write it here. It means the expectation, maybe I should say the distribution of so if I look at the average under G and the average under the disorder of I look at the overlap, the indicator function of the overlap between 2 points, to be larger than the minimum of the overlap between the other 2 points, so R1, 3 and R2, 3. This is 1. So said otherwise, it says so almost surely under the distribution G3, because this is a property of triangles. You take 3 points. Then you have R1, 2 is larger than the min of R1, 3 and R2, 3. So the distance. So since we know now by theorem 1 that we are on a sphere, this also means that the distance between sigma 1 under the same measure, so you pick 3 points under the Gibbs measure, under the measure G. You have sigma 1, sigma 2, and sigma 3, right? You pick 3 points. And you look under G3 independently. Then you average under the disorder. You look at their distances. Well, this says that the distance between sigma 1 and sigma 2 is always smaller. Remember the formula was there. The distance is given by something. The distance square is something minus R12. So every inequality for overlaps is reversed for distances. Smaller than the maximum, because you have a minus sign, this min becomes a max, of the distances between 1 and 3 and the distance between 2 and 3. This norm, of course, being the norm in the Hilbert space. So what does that mean? This means that the distance induced by the Hilbert structure on the support of the Gibbs measure is ultrametric. Right? So what does ultrametricity? Has somebody never heard the word ultrametric? Okay. Oh, Alex has not heard it. All right. So let me see. Okay, so maybe it's a good time to say that. All right, so forget everything I'm talking about here. This is a class in topology 101. So you have a space E equipped with D, which is a metric. So you know what a metric is. It's a function on E, which to a pair of points associate a number, which is the distance. It has to satisfy a few property. Right? So the distance, of course, so D is a function from E squared to R plus. It has to be such that distance of x, y is first it has to be positive. Second, distance of x, y is distance of yx. And third, distance of x, y is 0 if and only if x is y. All that is clear. But then you need the triangle inequality. That's what makes a metric. Okay, distance of xz is more than distance of xy plus distance of yz. That's the definition of a metric. You say that this metric is ultrametric, which means better than metric, if you have a stronger inequality. If the distance between x and z is smaller, instead of being smaller than the sum, it's smaller than the max. Yes. Right? Obviously, if something is smaller than the max of two numbers, it's smaller than the sum of the two numbers. So if it's ultrametric, it is metric. But ultrametric is a strange property. It's very strong. What does it mean? Okay. So anyway, first, you see that what I've said here is exactly that. It says if you take 2 points, in this, typically 2 generic points in the support, then the distances satisfy this, which is the ultrametric property. Right? That's exactly what I wrote here. So can I erase this now? I want to draw a picture. So as analysts, we tend to not very often deal with ultrametricity, right? Except when we deal with trees. But if we are doing more algebraic things, there are plenty of ultrametric things in the world. But we tend to ignore them when we have our background. Right? So if you never deal with prime numbers, you don't see many ultrametricity lurking around. Yes?
Why do you say trees are?
So yeah, we'll come to that. That's you'll see right now. The first thing to realize is that this property, so how can a triangle be if my space is ultrametric? Do it really. Try to draw a triangle. You will see something strange happens to a triangle. Just try. We have 3 points, x, y, z. Okay, so I have 3 distances. Oops. Say, I don't know, A, B, C. And I know now that A is smaller than the max of B and C. In my picture, it's okay. Right? So let's assume, just for, and without loss of any generality, I have these 2 numbers, B and C. So one of them is larger than the other. So here in my picture, C seems to be larger. Right? So assume, without loss of generality here, that B is smaller than C, smaller or equal to C. Right? So I have 2 possibilities. Here's a real line. I have C here, which is larger than B. And so the max is C here. And A is smaller than that. Now B can be wherever it wants, on the left of C. In my picture, B is somewhere here, but it could be here. Right? Okay, now apply the ultrametric property again for another not for A. Again, you have now, I don't know, C is smaller than the max of A and B. Right? So where can B, now we know that A is here, so where can B be? We have trouble here. Right? B cannot be here. So either A was equal to C. So let's assume that A is not C. Okay, so I assume that A is not C. If A is strictly smaller, so it's not equal, then necessarily B has to be C. Right? Because B cannot be above, we assume that it was below, and B has to be here. Right? And if B is not C, so that obviously, if B is not C, then A is C. Because that's what we have here. All right? So what I have proved here is that every triangle is okay, this is a word I can't say in English. There is no native English speaker here. Yes. In French, it's isocèle. What is it in English? Isosceles? Okay. So every triangle is isosceles. Every triangle has 2 sides that are the same. All right? That's strange geometry. You cannot draw a triangle like this. This is not an ultrametric triangle. Every triangle has 2 equal sides. Maybe 3, but at least 2. All right? So that's the core of ultrametricity. Every triangle is isosceles. I just proved it. Okay, now I have to be able to spell it. Something like that? No S here.
Don't ask me to spell it.
Okay, Google it. In French, it would be like this, isocèle.
I think you need to transfer that S to the end of the word.
What?
There's no S there, but there's an S.
Yeah, there's an S at the end.
Where do I put? And S here, isosceles. Okay, I know there was one more S than in French, but I don't know where. All right, so you all know what this is. It means two sides equal. So how can you create a metric which is like this? Can you think of one? That's easy. Take a tree. Here are the first instance of trees lurking in the picture. Take a tree. Not necessarily regular, any kind of tree. Right? And now look at, okay, maybe look at this. Okay, let's take it regular to start, and then we'll take a regular tree, now a finite tree. That would be simple to compute. Look now, because I want to have one generation here. Look now at all the leaves of this tree. Just the leaves. I could look at the whole tree, but let's look at just the leaves for the moment. And introduce the distance now between 2 points among the leaves here as being, essentially you look at how high you have to go to get to the same ancestor. So these two guys are at distance, this guy is at distance 0 from itself. These two are at distance 1 because they have the same father or mother, whatever. These two guys are at distance 1, these two guys are at distance 1, etc. But now this guy and this guy are at distance 2. You have to climb to their grandfather. Right? Now, these two guys here are distance 3. All right? This is a metric. This is an ultrametric. This is essentially every ultrametric is like that. And I'll explain why. So do you see that this is a metric? You just look at a genealogic tree and you count how many generations you have to climb up. So why is that ultrametric? Why is every triangle isosceles? Because in fact, you can create clusters. Here they are created naturally. You first create a cluster of all the brothers. You have clusters by brothers. Then you have clusters by being the grandchild of the same thing. So all these guys, so this is first one cluster, one cluster, one cluster, one cluster. And then this is a cluster, this is a cluster, and then the whole thing is a cluster. And then you could go on and have a larger family size. So obviously now a triangle is isosceles, obviously, because you take 3 points, and you cannot have, just try. It cannot work. Right? And, or if you want, you can just think of what this means. So on a tree, everything is, the natural distance on a tree is ultrametric. Now, how is that related to any other ultrametric space? Now, imagine that ED is an ultrametric space. Here is something that you can easily do. It's easy to introduce a tree structure. So I'm going backwards here. Here I give an example of a tree, saying the metric is necessary, the natural metric is ultrametric. Now I'm going backwards. I have an abstract, general, whatever ultrametric space, and I'm creating a tree structure. How do I do that? I say that I define an equivalence relation, x equivalent sub d to y, if and only if their distance is less than d. D is a non-negative number here. Okay? So and I'm saying this, because it's ultrametric, is an equivalence relation. With a metric, it's not true. All right? Because of the ultrametric thing here exactly says that this is an equivalence relation for any d. Right? What does that say? Look at the tree. It says level D is the level of generations you're climbing. So if I say that Alex and I are, have the same grandfather, then I and Alex have the same grandfather. Clear. So that's the property. The first property is trivial, the second too. But for the third now, if Alex and I have the same grandfather, and Oh, of course, it doesn't work for humans because we have two grandfathers. All right. All right. Okay, it doesn't work. But you get where I'm saying here. And Alex and Vladas have the same grandfather, then Vladas and I have the same grandfather. Okay? If we had only one grandfather. Okay. Of course, otherwise, okay, sex is always trouble. So if we were just parthenogenesis, that would be true. Okay? So that's, yeah, okay, let's not talk, let's be less, I want to have an example that works. So let's look at advisor. Okay, that only one. You never have two advisors mating to create a student happily. So I hope that, oh yeah, this is ridiculous. Beep. So you do the same thing now with advisors, and you see that it's clear. If okay, I can say that with Alex. Who's the advisor of his advisor? Yes, I know. All right. So if we have the same advisor of our advisor with Alex, and it has the same with Vladas, then Vladas and I have the same. Okay. So that's this equivalence relation. Once you have the equivalence relation, and you have, it's important thing is not that you have one equivalence relation. You have a whole family depending on D. D here is the level of generations, right? Because the distance here measures the level of generations. So when you have that, introduce the equivalence classes. I know them by C, I, or maybe a D here, and I. For a fixed D, I have equivalence relations, equivalence classes, which I can call CI, right? So they are here the clusters. If I fix D equals 0 here, what are the equivalence classes? The points. If I fix D equal 1, the equivalence classes are these guys. If I fix D equal 2, the equivalence classes are these two equivalence classes. If D equal 3, the equivalence class is the whole thing, right? But in general, it's always true. So these equivalence classes create a partition. They are clusters, if you want, which partition, because it's an equivalence class, for every D, there are clusters which partition the whole space. And when D increases, so of course, when D equals 0, they are just the points. It's the finer possible partition, which are just the points. When D increases, then these clusters cluster together, get bigger. Right? You have small clusters gathering into larger clusters. Right? So this creates a tree structure. This is exactly the tree structure. But the problem, you see this is a tree structure. This is what I'm drawing here. But there is a big difference between the two things I'm saying here. Right? What is the difference? Is that here, the distances were discrete. 1, 2, 3. And so it's easy to see what clusters means. And what clusters mean is easy, but it's easy to see how they merge. What is the structure of organization between the clusters? Whereas here in general, you have a continuum tree. This defines a continuum tree. What is usually called an R tree, a real tree, right? Because the parameter of branching now is in fact continuous. So it's a little more complicated to see what it is, but it exists, and there is a whole theory of that. But at least in one case, it's not hard. Imagine that the distribution zeta, so now going back here, imagine that zeta is discrete, right? Which means the values of the overlap are discrete. And remember, this is how we describe the Parisi formula, from discrete overlap structures. If zeta is discrete, then the value of the overlap are discrete, the value of the distances are discrete, so this ultrametricity here is of that type. So when zeta is discrete, what this theorem says is that there is really a discrete tree. The support of the Gibbs measure is a discrete tree. That's what it says. Right? I mean, you have points, and it's clear that by that I mean that the organization of their distances is like a discrete tree. So how can you see a tree on the surface of a sphere? Right? That's the geometry. So by the way, when the support of zeta is discrete, we say that there is a replica symmetry breaking of finite order. And what is the order? Remember what it was? It was the number of possible values of R. Right? That is the size of the support of zeta. The number of possible values of the overlap is simply the number of generations in the tree. So if you have replica symmetry breaking over order 1, it means you have a tree, remember, because there was a shift of 1, a tree with 2 levels, one more including the top. So this would be replica symmetry breaking over order 1. This would be replica symmetry breaking. This would be replica symmetry RSB, RSB2, etc. That's the Parisi ultrametric structure. What is absolutely fundamental and fascinating in Parisi's picture is that if you take the Sherrington-Kirkpatrick model, P equal 2, what is expected is that zeta is supposed to have a continuum support. So you really have a continuum tree somewhere. If you take a p-spin model with p larger than 3, it is expected that, remember our Gibbs measure depends on temperature. It is expected that at low temperature, but not too low, you have a finite tree, which means finite replica symmetry breaking, in fact, one-step replica symmetry breaking. And at lower temperature, you have a full continuum tree. Now, when you make a mixture of them, just guess. All right, so that's where, so I just asked, so this gives you the whole picture, except for the moment we have no, let's assume even that we could prove all these nice theorems. How do you prove that Ghirlanda Guerra is satisfied for our models? Right, you have to prove that. So the nice part is that, oh, before I go there, I was just asking the question. How do you put a tree on a sphere? Okay, a tree, so okay, here is a sphere. I'm trying to do something. Okay, that's a sphere in infinite dimension. And now you have a measure carried by that, a random measure. Let's assume just for the moment that this random measure is discrete, as a discrete support. Right, so you have points. That's the support of this measure, and weights somewhere. My random measure. Wait. How can that be a tree? Right. The idea is, in fact, you should think that this measure is essentially carried by, it cannot be organized like this. Here's a way to create a tree, an ultrametric structure. I first take points on my sphere, maybe this one, maybe this one, maybe this one, maybe this one, and I give weights to these points. The same weights. Say weight 1 in green. The same weight to all these guys. I'm sorry, not the same. Drawn 1, 2, under some random distribution. All right. Now, around each of these points, so then the distances between these guys has one given, one distribution. So this is obtained. This is a sample of one distribution. Then around each of these guys, I do the same thing. I choose now red points, which are at a certain distance from this guy, typically. And on these ones, I put another weight. Let's say, I don't know, U. Here it would be 2, 1. U, 2, 2. U, 2, 3, etc. Right? That is, in my index here, I remember that this is in group number 2. And then I have the second index, which is first guy in group number 2, second guy in group number 2, etc. And I can go on, but let's stop here. And you do that around each of these points. And now, what is the, now I forget the green guys. I don't use them. I'm looking at the measure just on the red guys. And how do I define the measure of such a guy? I just add this plus that. Maybe with coefficients if you want. Right? This will give me something which will be ultrametric. That's for the measure. Otherwise, for the distances, you see, right? What is the distance, the property of the overlap or the distance between two such points? Either I take points here which are in the same group, and their distances are essentially the same. Or I take one guy in one group and one guy in another group, and their distances are essentially given by the distances of these guys. Right? And so that's a tree. You know, in order to create a tree, every tree is a family tree. So you just create a family structure. Right? You put the grandfathers, then the fathers, and then you could put the sons. Okay? And that's what is supposed to happen for spin glasses. For a discrete structure, you can see that easily when you have finite replica symmetry working. When it becomes to be continuous, of course, it's harder. So, great. Next time, we have to see at least, so this theory is very nice. For the moment, it's absolutely not related to spin glasses because we don't know how to prove Ghirlanda-Guerra or even an approximate version of Ghirlanda-Guerra. So I need at least, here's an interesting question. One example of a G satisfying Ghirlanda-Guerra. This whole theory is beautiful, but if it's never satisfied, what can we do with it? Right? So even before trying to say that it says something about spin glasses, I'm asking, do we know one example? Just one. Okay? The answer to that is really fascinating. If you want to have one example, since you know that you will end up having something with positive overlaps and ultrametric structure, and essentially one distribution for the distances, why don't you start from a tree? Right? Of course, you have to embed it in a Hilbert space, but that should not be too hard. Because these points are supposed to be on the sphere like I was drawing here. So it's not hard. You take a basis of your Hilbert space. Here you say this is one, and this is associated with one vector of the basis to another one, points in this, whatever. Putting it on the sphere is not hard. You start from a tree, and you ask yourself, when is it that if I do this, with random kind of weights, I have to put weights on them, those things I call W and whatever. Do I have a way to put weights on a tree where, in the end, I have the Ghirlanda-Guerra thing? All right? And so, not clear. And the answer is, use the REM. That's the answer for physicists. Let's use the random energy model. The answer for a mathematician is use Poisson-Dirichlet, which is the same. So I will next time explain what the Poisson-Dirichlet cascades or Poisson-Dirichlet process first is, and then the Poisson-Dirichlet cascade, which are also called the Ruel probability cascade, and then what their limits are, and we will see that these guys have, so these guys are absolutely natural objects in REM, of course, is naturally related to that, but let's forget REM for the moment. The Poisson-Dirichlet process is a very, very simple object in probability. A priori, it has nothing to do with our problem here. And then, of course, we will see that it satisfies Ghirlanda-Guerra. And not only it satisfies, but essentially, that's the whole story. Essentially, any guy can be any. So I could even go a little further. This is one nice thing. One example. One example would be too easy, maybe. So fix zeta, I make my question a little more complicated. I fix the functional order parameter, zeta, one probability measure. Does there exist one example of a G satisfying G with functional order parameter zeta? This is now more difficult because now I have a whole class of examples. I give you one probability measure, which is the distribution of the distances. Can you construct one Hilbert space, one G, with this thing, which will satisfy Ghirlanda Guerra? So of course you want the zeta to be carried by the positive numbers. Then the whole distribution of the array will be determined by zeta. But the question is, can you construct something which satisfies Ghirlanda Guerra? Then it will be ultrametric. The idea is use Poisson-Dirichlet. And then we'll see, for every zeta, there will be Poisson-Dirichlet cascades. The structure of the cascade, which means the tree, will be determined by the structure of zeta. And you see how. Let's imagine for a moment that zeta is discrete, as 17 atoms, then the cascade will have 17 levels. And then the structure of the weights that you put on them will be, of course, determined by zeta. There's a way to do that, which is to use this Poisson-Dirichlet cascade, which is a very, very natural and very old object in probability. It doesn't come from spin glasses. It's much, much further. And once we've done that, we'll have created this whole class now. For every zeta, you will have a class of nice measures. What is fascinating is that, in fact, all the measures coming from spin glasses are in this class. Okay? Saying that is stating the Parisi ultrametric conjecture. Saying you start from something which has nothing ultrametric. When you start from our model over there, it's not ultrametric. There is no tree structure, no hierarchical structure in the covariance. There's nothing hierarchical. And at low temperature, what emerges is a tree, that is a hierarchy. That's the ultrametricity conjecture. Okay? And we know now that if we can prove that the limiting object is Ghirlanda Guerra, it will be it. All right? So then, of course, the thing is to prove Ghirlanda Guerra, at least in an approximate fashion for Gn. How do you prove Ghirlanda Guerra for the limiting object? You prove something for Gn, and then try to go to the limit. Right? Next time.